We now move to the second part of the webinars, the integrate emission calculation models in your journey planner. Haris Kouridis and Martina Castori will show us how that can be done. Martina, you are the presenter now.
Thank you. Just a moment to
click on show my screen.
Can you see our screen now?
Yes.
Okay.
So, hello. My name is Haris Kouridis from EMISA. I would like to show you how to integrate the emission calculation model in any journey planner. Of course, I will try to explain a little bit what an emission calculation actually is and what this means for a journey planner and how we integrate it, how we decided to integrate it in GIM and what you can do in your journey planner as well. So what I'm going to present is the calculation algorithm, the basic calculation algorithm, and I will also explain why we needed to use indicators rather than direct emissions for the quantification of the emissions in case you want to apply them in your journey planner. So the first and most important thing is that the energy requirements are directly connected to the CO2 emissions. So if you want to reduce CO2 emissions, actually what you want to do is reduce your energy requirements. If you reduce your energy consumption by 50%, then your CO2 emissions are also reduced by 50%. Now, in our calculation model, we have assumed that all fuel carbon is 100% transformed into CO2. What this means is, in a very basic and simplistic approach, if you want to move a certain mass from point A to point B, you need an energy. There is an energy requirement for that. You require the energy in order to overcome the opposing forces to that movement. This energy, in the case of transport, comes from the fuel, and you burn the fuel, an equal amount of fuel to the energy that is required, and this fuel is then transformed 100% into CO2. And as I said before, it's actually this is the most important thing of this presentation, is that what you do if the CO2 emissions are directly connected to the energy or in this case fuel consumption. Now, what are the opposing forces in case of road transport? It's of course the friction which happens in the engine and on the road. It's the engine efficiency. As we know, internal combustion engines have an efficiency of around 30–40% depending on the engine. There is the air resistance, which is very important, of course, when you're traveling at high speeds. It's the road condition, it's the road inclination. So if you go uphill, you need much more energy than if you're going downhill. The vehicle weight, of course, and the different energy that the systems in the car use. So it's can be the air conditioning, it can be the lights, it can be the stereo, anything that you have that requires energy within the car, which is, if you add this up to many cars, quite significant. Now, this, as you can imagine, is a very complex system for an analytical solution to be found. What we do is we use an experimental approach. We get the results, and these results are then transformed in a methodology. Where we do these measurements? We do laboratory measurements, we do engine dynamometer measurements, vehicle dynamometer measurements. The difference between those two is an engine dynamometer is a dynamometer that you only attach an engine to it and you make the measurements, while a vehicle dynamometer, you get the whole vehicle, and that's the bottom page, the bottom picture in this slide. You get the whole vehicle, you put it in the laboratory on rollers, and then you measure the emissions and the fuel consumption from this vehicle. And finally, it's the PEMS measurements, which are portable emission measurement systems, where you do measurements on the road. So we collect all this information and we transform this into our calculation methodology. Now, what actually we get is every time we do a measurement, we get a point on this graph. Then we combine all those points to get an average function that describes each time a different, let's say, a different pollutant or a different characteristic. So in this specific image, what you see is the CO2 emissions of a gasoline vehicle in grams per kilometer. On the horizontal axis is the average speed of the vehicle, so how fast it is traveling, and on the vertical axis is the CO2 emissions. It's a very typical pattern where on low speeds you have increased emissions, and as we said before, increased CO2, increased energy consumption, and on higher speeds what you get is again increased energy consumption and CO2 emissions, because of one very important factor, for example, is the wind drag. So at the end, if you want to calculate the energy consumption, what you do is you multiply this factor by the number of vehicles and the mileage that they drive. So you get, for example, 80 grams per kilometer times the number of vehicles times the mileage driven by those vehicles, and you get the total CO2 emissions or energy consumption. Now, there are, of course, some additional parameters that you can take into consideration if you want to be a bit more, to make your calculations a bit more targeted. What you can do is you can do specific projects that deal, for example, they can quantify the effect of the inspection and the maintenance of a vehicle. So if I maintain my vehicle, do I improve my emissions? Does this have an effect on my energy consumption? So there are targeted studies that show that. You can do a literature review where you can combine findings from other sources, or what you can do is, although it is a rather complex system, and I believe that we've established that, however, sometimes it is very expensive to do a multitude of measurements. So what we do is we combine the findings that we have in a laboratory with micro-modeling. And the micro-modeling takes into consideration the vehicle load, the road condition, humidity, the ambient temperature, the road slope, and you get the same, you can construct then similar function as these to fill the gaps where your measurements are missing. Now, if we have applied this methodology into the platform, and this is an example. You want to travel from Larissa, let's say, which is a city in Greece, to Thessaloniki, and you're going to travel with a bus, which is a Euro 6 bus. The distance is around 180 kilometers, and the average speed will be around 80 kilometers an hour. This means that you get an average fuel consumption factor of approximately 360 grams per kilometer. If you multiply this with the distance, and of course it's only one vehicle, what you get is that you will require 64 kilograms of fuel, and then you can calculate after that how much CO2 is emitted. Of course, this will be, let's say, the conclusion of this presentation. This does not necessarily mean that the bus is a good or a bad means of transport. Because if you compare a bus with a train that will do the same distance, of course, the train will consume much more fuel. but you need to consider how many people are traveling with the bus and how many people are traveling with the train. So what you actually need is to see if it is more efficient in terms of transport activity to travel with a bus or with a train. So what we have introduced here is the fuel consumption or CO2 emissions per passenger kilometer. So if we take, for example, this number, which is 64 kilograms, and divide it by the number of passengers on the bus, you get this indicator. And in order to evaluate, to be in the position to evaluate if a bus is better than a train, you get the same, you do the same calculation for the train, then you calculate the indicator, and then you can propose if the user, if the passenger should use the bus or the train if he wants to be more environment friendly with his transport. And I think this is the conclusion of my presentation. Thank you very much.
Thank you, Haris. If anyone has any questions for Haris and Martina? If not, I'm going to proceed to part 3.